you know the exact moment your training run is doomed.
Oh, absolutely.
Like you are pushing a reasoning model to its absolute limits, trying to get it to output this massive chain of thought for a complex mathematical proof. You scale up the thinking tokens, you watch the GPU memory utilization climb, and then bam!
You hit the wall.
Exactly. You get that dreaded out-of-memory error. Or, I mean, best case scenario, your throughput just grinds to a complete halt because the KV cache has consumed all the available VRAM.
Yeah, the computational tax of quadratic attention is just unforgiving. For every single new token the model generates, the attention mechanism has to, compute scores against every previous token in the sequence.
Right.
So when you're dealing with reasoning traces that stretch into the tens or hundreds of thousands of tokens, that quadratic scaling curve essentially becomes a vertical wall.
Well, welcome to your custom deep dive. Today, we're looking directly at the stack of research you sent us regarding these massive compute bottlenecks in AI reasoning.
A very timely topic.
It really is. And your core source today is this groundbreaking paper from researchers at Milad, Microsoft Research, McGill University, and a few others. It's titled The Markovian Thinking, Architecture-Agnostic Linear Scaling of Reasoning.
It's quite a title.
Yeah, and our mission for you today is to dissect exactly how this team fundamentally restructured the reinforcement learning environment for reasoning LLMs, because they essentially completely bypass this quadratic bottleneck.
I mean, the proposition in this paper is a true paradigm shift for anyone working in machine learning or data science. They achieve linear scaling of compute and strictly constant memory usage without altering the underlying transformer architecture at all.
Right, without touching the transformer.
Exactly. We are talking about redefining the underlying Markov decision process, or the MDP, used for reinforcement learning from verifiable rewards. It basically allows a model to think for 1 million tokens with linear cost.
Okay, for anyone who has spent weeks staring at PyTorch profilers trying to optimize KV cache usage, 1 million token thought process with linear scaling sounds like pure magic.
It does.
But to understand the cure, we really need to rigorously define the mathematical disease here. So let's look at the baseline RL formulation for long chains of thought, or LongCoT.
Right. So if we break down standard reinforcement learning from verifiable rewards, the fundamental limitation is hard-coded right into the basic environmental setup.
Okay.
In standard LongCoT, the MDP state at step 2, which we'll denote as unpoor, is simply defined as the concatenation of the initial prompt and all the generated tokens up to that point.
So sandaled X plus YT.
Exactly.
Which, I mean, on the surface, that seems mathematically necessary. You want the policy to be conditioned on everything it has derived so far. Right?
So that's a standard intuition.
But the structural flaw there is that the state is unbounded. The size of state is on onti. It grows linearly with every single generation step.
And when you map that unbounded state onto an attention-based policy, the hardware implications are severe.
Yeah.
Generating a final token for a responsive length dollar incurs a context size of $6 plus 1 over 1. This mathematical reality forces an overall computation cost of S2 arents relative to the number of thinking tokens, where $6 is the scaling factor of your sequence length.
And that just completely cripples scalability for both training and inference. The KV cache just keeps growing, taking up all that precious high bandwidth memory.
It heavily bottlenecks your ability to process parallel requests.
Yeah, it's like trying to solve a complex math proof on a whiteboard, but the rules of the environment dictate you're never allowed to erase anything.
That's a great way to put it.
To write the next line of the proof, you just have to keep buying infinitely larger, exponentially more expensive whiteboards until you run out of wall space, or in our case, until you run out of H100s.
And standard workarounds in the literature usually attempt to sidestep this by just limiting the length of the thought itself.
Like pruning.
Yeah, techniques like length-regularized objectives, sparsity pruning, or early exit methods. They all try to save that whiteboard space by forcing the model to stop thinking so much.
But they are fundamentally still operating inside that restrictive quadratic regime.
Precisely.
Okay, but I have to push back on the core premise here. Isn't having the entire historical trace mathematically necessary for the architecture?
How do you mean?
Well, if an attention head is trying to track logical steps across a 20,000 token math proof, my intuition says it needs to be able to attend directly to the variable it defined in step 1 while it's calculating step 50.
That intuition is exactly what the researchers decided to challenge here.
Oh, really?
Yeah, they hypothesized that the full exhaustive trace is not strictly necessary for progression. provided the model can synthesize its current logical state.
Ah, okay.
So instead of modifying the transformer's attention mechanism, they modified the RL environment itself. They proposed this paradigm called Markovian Thinking,
Right.
where the policy advances reasoning while conditioning on a strictly constant size state.
And they instantiated this concept with a specific RL environment they called Delethink. So how exactly does the Delethink environment stop the whiteboard from expanding indefinitely?
It artificially caps the state size by structuring the reasoning trace into fixed-size chunks.
Okay, chunks?
Let's say we establish a context budget of $8,000 tokens. Within that 8K chunk, the model generates tokens exactly as it normally would. It attends to everything in that local window.
Normal behavior so far.
But the critical transition dynamic occurs right at the chunk boundary. When the context reaches 8,000 tokens, the generation just halts.
Right. The environment intervenes and completely resets the context. It reinitializes the prompt with the original query $1 plus a short carryover segment from the very end of the previous chunk.
Yes.
And this carryover is the Markovian state, denoted as dollars. In their primary experiments, dollars is set to half of the context budget, so exactly 4,000 tokens.
Exactly. And the older reasoning tokens, everything generated before that 4,000 token carryover window, are permanently truncated from the prompt. Just gone.
Yeah.
The policy can no longer attend to them at all. Through the RL training process, the model must learn to explicitly write a textual summary or a concentrated logical state near the end of each chunk.
Right, and that text must contain all the necessary mathematical constraints and intermediate variables required to seamlessly continue its reasoning after the environment resets its context.
You've got it.
This is why we need to dive into the mechanism of the reinforcement learning, because this is fascinating to me. How does the model actually learn to write a high-quality handover document to itself?
It's a great question.
Because it's not like there is a supervised data set of good 4K summaries out there to train on.
No, there isn't. The learning signal emerges entirely from the verifiable reward at the end of the entire multi-chunk trajectory.
Okay.
The researchers use group relative policy optimization, or GRPO, for the advantage estimation. When the trajectory eventually finishes, the final answer is checked against the ground truth.
Right, the verifiable part.
Exactly. If the answer is correct, a positive reward scalar is applied. If it's incorrect, the reward is 0 or negative.
So if the model writes a terrible handover state in chunk 1, chunk 2 will inevitably fail to reach the correct final answer.
Right.
That failure results in a negative advantage for the whole trajectory. And because GRPO updates the policy based on the log probabilities of the generated tokens, the tokens that form that poor handover state in chunk 1 get their probabilities downweighted during the gradient update.
The environment structure handles the credit assignment beautifully. RL just naturally optimizes for the expected return.
Right.
To maximize the return, the policy discovers that it must arrange its latent thoughts into a highly dense, informative textual state right before the boundary hits. That ensures the next chunk has the exact conditions needed to proceed.
Man, let's unpack the math of the linear scaling here, because the hardware savings are essentially the entire value proposition of the paper.
Yeah, they're huge.
The effective state the policy reads is now strictly bounded at OC. So if you want to scale the model's thinking from null tokens up to nullis tokens, you aren't squaring the context length anymore.
No, you're not.
You are just running $2 chunks sequentially.
Bounding the context forces the FLOPs to drop dramatically. In the baseline LongCoT environment, scaling the thought length gives you OHN2 SLOPs.
Right.
Under Delethink, the compute required drops to non-NOP. The scaling becomes perfectly linear with respect to the thought length.
Now, looking closely at their FLOPs equation in the paper, I do see a constant factor of 2. It is OLP.
Yes.
If I'm reading this correctly, that is because a portion of the tokens are essentially processed twice, right?
Correct.
Once during the decode phase when they are generated in the current chunk, and once during the prefill phase when they are re-encoded as the new prompt for the subsequent chunk.
Yeah, passing the Markovian state forward physically requires clearing the KV cache at every boundary. Those carryover tokens are no longer in memory. So they must be reprocessed through the model's forward pass to rebuild the KV cache for the new prefix.
But the prefill operation is incredibly highly optimized on modern inference engines, right? Like SGLang.
Oh yeah, it is highly parallelizable.
So that minor computational penalty of re-encoding 4,000 tokens is just vastly outweighed by the fact that your KV cache clears entirely at every boundary. your memory footprint remains strictly constant.
Exactly.
You never, ever exceed that 8K budget in VRAM, regardless of whether the model thinks for 8,000 tokens or 800,000 tokens.
Decoupling the thinking lengths from the context size essentially solves the memory wall. But, a mathematically elegant environment is completely useless if the aggressive truncation destroys the model's actual reasoning capability.
Yeah, theory is cheap, right?
Right.
If you force a large language model to repeatedly amputate its own context window, my immediate assumption is that its accuracy on complex benchmarks is just going to plummet.
It's a fair assumption.
So let's look at how they actually trained this and what the benchmarks say. They utilized R1 Distill 1.5b, which is a very strong foundational reasoning model, and trained it on the DeepScaler dataset, consisting of about 40,000 highly curated mathematical problems.
And evaluated against the AIM 2024 and AIM 2025 benchmarks, which, as you know, are extremely rigorous math competitions, Delethink demonstrated zero degradation.
Wow, zero.
Zero. Running in 8K chunks, the Delethink model matches and even slightly surpasses the baseline LongCoT-RL model that was trained with the same total 24K continuous thinking budget.
That's incredible. The policy effectively learned to reason at an elite level despite having its history constantly wiped.
It did. And the compute cost realities attached to those benchmarks are just staggering. The researchers provided the hardware metrics, and they paint a very clear picture.
Let's hear them.
To train a model to generate an average of 96K thinking tokens per problem under the standard LongCoT-RL setup, it requires an estimated 27 H100 months of compute.
27 months.
With Delethink, achieving that exact same 96K average reasoning length costs just 7 H100 months.
Wow. And the divergence in computational efficiency only accelerates as you scale further out, right? If you push the target up to 1 million tokens, Delethink achieves a 17x reduction in FLOPs compared to the LongCoT baseline.
Exactly. It's massive.
That is the difference between an experiment being feasible for a mid-sized lab and being financially impossible for anyone outside of top-tier tech conglomerates.
Absolutely.
But it actually gets even more interesting when we look at test time scaling limits. This is a critical phenomenon the researchers documented that goes beyond just saving money.
Test time scaling really is the ultimate proving ground for this method.
Right.
If you take a standard LongCoT model that was trained on a 24K token budget, and during inference you allow it to think for 48K or 96K tokens, its performance flatlines?
It just stops improving.
Its accuracy on AIM 25 stops improving right around that 24K mark because the model enters an out-of-distribution state. It has never seen positional embeddings or attention patterns that long during training, so it becomes confused.
But because Delethink processes everything in strictly fixed 8K chunks, it fundamentally never encounters a sequence longer than what it saw during training.
Right.
It exhibits true sequential test time scaling. It just keeps passing the baton. The benchmarks show it continues to improve up to 128K tokens and beyond.
It really does.
The paper explicitly notes it successfully solves incredibly hard AIM 25 problems at lengths of 140K tokens, problems that simply cannot be cracked at shorter inference length.
And think about what that means. 140,000 token reasoning trace using 8K chunks means the model is executing over 17 context resets.
17 resets.
It is perpetually maintaining, updating, and refining its logical state across 17 distinct transitions without losing the mathematical plot.
Okay, let me play devil's advocate for a second here, because I know practitioners listening to this will have the exact same thought.
Go for it.
This Markovian state passing makes logical sense for mathematics. Math is highly reducible. You can easily summarize, I have proven X, now I need to derive Y using constraint Z.
Sure.
But what about tasks where you absolutely need the granular historical context? Take software engineering. If you are on line 500 of a complex script, you might need to perfectly reference the syntax of a custom variable you defined on line 12. Does deleting the history break the code generation?
The researchers actually anticipated this exact concern regarding out-of-distribution generalization. To rigorously test it, they evaluated the Delethink-trained models on tasks they were not explicitly trained on.
Oh, nice. Like what?
Specifically, GPQA Diamond for graduate-level physics and chemistry and Live Code Bench for code generation.
Yeah.
Surprisingly, Delethink still matches the LongCoT's baseline on these tasks.
Wait, it matches the baseline on Live Code Bench without being able to attend to the early code blocks. How is that mechanically possible?
The model actively learns to carry forward the raw material it anticipates needing.
Oh, wow.
Through the generalization of the RL process, the policy learns to embed highly specific early variables, function signatures, or syntactic constraints into its Markovian state before the chunk boundary hits.
That's wild.
It dynamically adapts its writing style based on the domain to ensure the survival of critical information across the context resets.
It adapts its own context to act as a highly specialized cache. That is amazing. But, this brings up a massive question regarding the training dynamics.
Which is?
If Delethink forces models to learn a totally alien way of thinking, writing predictive handover documents to themselves, why is the RL training so stable right out of the gate? Usually, if you radically alter the MDP of an environment, the model thrashes violently at initialization because it has no prior concept of how to maximize the reward.
Yeah, the stability at initialization leads us to perhaps the most fascinating analytical finding in the entire paper.
Yeah.
The researchers apply what they call Delethink tracing to off-the-shelf models in a purely zero-shot manner.
Meaning no training.
Right, this means no RL training, no specialized prompting, and no fine-tuning. They just forced the raw models into the Delethink chunking environment at inference time.
And they tested this on a wide variety of architectures and scales, right?
Yeah.
From the R1 to still 1.5B, all the way up to massive parameter models like GPT-OSS 120B and Qwen 330B.
Exactly. And what the data revealed is a phenomenon they term latent Markovian behavior. Even at step 0, without any exposure to the chunked MVP during training, these off-the-shelf models already sample Markovian traces successfully.
Wait, really?
Yes, when subjected to the aggressive context deletion of Delethink tracing, they recover, or in some cases even exceed, their standard LongCoT baseline performance.
So an off-the-shelf 120 billion parameter model, which has never been explicitly optimized to condense its thoughts into an 8K chunk, can just natively survive having its context deleted mid-thought. Mechanically, why does that happen? Where does that capability come from?
The paper offers a highly compelling hypothesis rooted in the pre-training data distribution.
Yeah.
These LLMs are pre-trained on vast corpuses of human reasoning traces, textbooks, academic papers, and code bases.
Right.
And human reasoning is intrinsically Markovian because our biological working memory is strictly bounded.
Oh, that makes sense.
When a human author is solving a complex equation on page 20 of a physics textbook, they explicitly carry forward intermediate equations and core constraints into the local text. The author doesn't continually reread pages 1 through 19 to remember where they are.
That makes perfect sense. We naturally write in a way that carries the necessary context forward locally.
Exactly.
So the models have already mapped this Markovian state-passing behavior simply by modeling the conditional probability of human text. The RL training doesn't have to build the capability from scratch. It already has a dense distribution of positive in-distribution samples to learn from.
Yes, the RL is merely reinforcing a latent structural capability. Man, the pre-training distribution acts as a massive prior that stabilizes the RL fine-tuning. That's elegant. However, to truly utilize this effectively in practice, we have to look closely at the hyperparameters, specifically the context size. See $ablations.
Oh, right. The ablations are key.
Because the researchers tested the limits of how tightly they could squeeze that chunk window before the latent behavior collapsed. We know seed8-Kalers is a highly stable operating point. That was the configuration for their main training runs.
They also evaluated CC4K dollars, keeping the total overall thinking budget normalized at 24K tokens. And C4K dollars proved to be surprisingly effective.
Really?
In fact, for the smaller 1.5B parameter model, a 4K context window sometimes scaled even better than 8K on both the AME and LiveCodeBench datasets.
But when they pushed the ablation down to CT2K dollars, the performance utterly tanked.
Huh.
The reasoning traces degraded significantly. Why does a 2,000 token window break the model so completely?
It's a tricky issue. Is it simply a capacity issue? Like 2,000 tokens just physically isn't enough vector space to hold the Markovian state and still make meaningful forward progress on the problem?
The failure mode at 2K is much more nuanced than raw capacity. It is fundamentally a horizon problem related to the underlying architecture.
Okay, a horizon problem.
We have to consider how positional embeddings, specifically rotary position embeddings or ROPE, function in a transformer. They give the model a mathematical sense of how long it has been generating text within a sequence.
Right.
At a highly constrained 2K context size, the model is constantly hitting the boundary, meaning the environment is constantly resetting its positional embeddings back to 0.
Ah, I see. So from the perspective of the attention mechanism, it perpetually feels like it has just started talking.
Exactly. Because of this incredibly short local horizon, the predictive signal to conclude the thought to allocate high probability mass to an end of sequence, or EOS token, gets completely overwhelmed by the local bias to just keep expanding on the current point. The researchers observed that the EOS generation rate absolutely plummets at the 2K setting. The model just rambles indefinitely. It can't converge its reasoning to finalize the mathematical proof because it lacks the positional awareness of a long trajectory.
So there is a clear lower bound. 4K to 8K seems to be the necessary sweet spot for current architectures to maintain enough of a positional horizon to reach a conclusion without wasting unnecessary compute on quadratic attention matrices.
Yeah, the ablations prove that while complex reasoning can be structurally transformed into a Markovian process, you cannot infinitely compress the transition frequency before the model loses its sense of progression.
By redefining the RL environment to fully decouple the length of a reasoning trace from the context size of the attention mechanism, the Markovian thinker provides practitioners with a validated blueprint for architecture-agnostic linear scaling of reasoning.
It represents a massive efficiency unlock. It proves that the RL environment itself, which we usually treat as a fixed, trivial wrapper around the model, is actually a highly powerful lever for algorithmic progress.
It saves vast amounts of high bandwidth memory by keeping the KV cache strictly bounded. It drastically cuts hardware requirements, dropping a 27-month H100 training run down to just 7 months.
It's incredible.
And crucially, it unlocks test time scaling far beyond your training budgets because the model never encounters an out-of-distribution sequence length. It just sees another perfectly formatted 8K chunk.
Right.
You know, before we wrap up this deep dive, there is a fascinating implication buried in the theoretical appendix of this paper that completely rethinks AI hardware and infrastructure.
Yes, the KV state MDP.
Exactly. Throughout this discussion, we've talked about Delethink passing the Markovian state forward as explicitly generated text. It generates the tokens, the environment resets the prompt, and it feeds those literal tokens back in.
The researchers implemented it via text space because that is what current distributed training infrastructure like PyTorch FSDP and current inference engines like SGLang natively support. It requires zero custom CUDA kernels.
Right.
But the authors briefly theorize what they call a pure KV state MDP.
What if we define the RL state purely as the raw KV cache entries? Imagine redesigning our GPU kernels so the model never has to explicitly decode and write out its carryover state into English or mathematical text at all.
Instead of paying the computational tax to auto-regressively decode the state and then pre-fill it back into the network, you would perfectly pass the raw, latent logical state, the high-dimensional internal KV activations, directly across the chunk boundaries in memory.
That would be insane.
It would essentially be differentiable state passing without the sequence length growth. It could completely alter the fundamental infrastructure of reasoning models, making this linear scaling paradigm orders of magnitude faster.
It points to a future where we could eventually train models that natively think for millions or tens of millions of tokens entirely in highly compressed latent space without ever hitting a memory wall. We finally get to erase the whiteboard.
A very exciting prospect.
Well, thank you for joining us on this highly technical exploration. We highly recommend you read the full paper, The Markovian Thinker, and check out the open source code and model weights provided by the McGill NLP and Milad teams to test these linear scaling limits on your own hardware.